All right, so I want to first thank the organizers for this wonderful workshop, and it's a pleasure to see a few familiar faces as well as many, many new faces. I also want to thank Christian for that excellent talk, giving an example of synergy between different kinds of observations. Also, for his dress code, since he is 5 sigma above the normal, I can wear a t-shirt now. But this is a very important t-shirt because this is a t-shirt for the Plateau mission, which for at least some of us is still very far in the future, but for many of you is going to be one of the major missions which is going to be epical for your career, I think. And it's not, of course, the only exoplanet mission out there, but it will be one of the ones that will, I think, change the history of exoplanet science and probably tremendously influence your science in your careers. So a little retrospective here. I'm sure many of you, how do you use this? There we go. Many of you know the person shown here on the right, for whom this workshop is named. But in addition to Carl, I want to introduce somebody you might not know, Professor Bruce Murray, who was on the faculty here and was director at the Jet Propulsion Lab for a number of years. And he played a major role in the exploration of our solar system by robotic spacecraft. And the 50th anniversary of that exploration, at least the photographic exploration of our solar system, was just actually a couple weeks ago. Actually, on the very same day that the spacecraft, the New Horizons mission, flew by Pluto, was the very same day, exactly 50 years before, that Mariner 4 flew by Mars and returned the first images of another planet from a spacecraft. And Bruce was on the camera team for that. And I think the exploration of Mars, which changed our picture of the solar system, as well as the set aside a lot of preconceptions about what other planets might be like, is very telling in terms of, and might be very useful for our understanding of exoplanets. It's also, I think, a cautionary note about what we know and what we really don't know about exoplanets and their properties. I think it's very useful to keep in mind this aphorism by Carl, who clearly urged us to separate what we clearly know as established fact, or clearly a number which we have well quantified, versus that which is much more speculation. And I hope I'm getting the message across by showing this statement about separating fact from speculation with a picture of the latest announcement of a planet around another star, which is in the habitable zone and which may or may not resemble anything like the Earth, not even saying something about its habitability. And that'll be actually one of the little take-home messages of my talk today. So back to Mars, which I think really Mars is on the road to exoplanets in a way, not the other way around. The first Mars encounter, as I said, was just over 50 years ago, and returned to images, as some of you probably know, of a crater, almost lunar-like surface, which was quite different from what we had sort of hoped, but was actually at the sort of end culmination of a large number of ground-based observations, which began to describe a world which was very different from what we had thought of just a few decades earlier. And the scope of our ignorance is represented, for example, by this 1962 US Air Force map, which was actually used to plan the flyby of the planet by Mariner 4 in terms of where we would want to time things so that we could see these dark markings. And on this map are still the canali of Mars, sort of an inheritance from Schiaparelli and Percival Lowell and countless ground-based observations. But fortunately, those weren't the only ground-based observations. We already had a picture of Mars that was changing, and which included some aspects which I think sort of might remind us of the kinds of things we're encountering with exoplanets today. And some of these observations, actually many crucial observations, were performed just on the mountain that you can see above us, Mount Wilson. 2 telescopes up there contributed to this, the 60-inch and the 100-inch. The 60-inch was used during the last good opposition of Mars prior to the Mariner 4 encounter. to take these high-resolution images of Mars. No adaptive optics, obviously, but nevertheless, in good seeing, which is what this area is blessed with, at long wavelength observations, orange, or about 700 nanometers, these observations clearly showed distinctive features on Mars, which people such as Harold Urey actually correctly interpreted as being probably associated with lava fields. And also the fact that if you observe Mars most of the time at bluer, much bluer wavelengths, say 400 nanometers, you tended to see absolutely nothing. There was some sort of haze that was blocking everything, and we basically just couldn't see through that haze at that wavelength. And this may seem very familiar to those of you who struggle with transmission spectroscopy of exoplanets. And then, speaking of spectroscopy, the 100-inch was used to actually obtain spectra of Mars in search for the atmospheric constituents, which were very difficult to see with that technology at that time. And before you say, oh, I can see this, these, in the spectra, these features are iron lines in the sun. They are not what you were looking for. The features of CO2 and eventually of water, which was detected from Mount Wilson, as well as from Switzerland, are these very indistinct features here at this level of instrument resolution and signal to noise, at least. But one of the things that was well known about Mars, actually fairly precisely known by this time, was the mass and the radius. So unlike the atmospheric properties and what was causing the seasonal changes on Mars and whether or not there were plants on Mars versus a completely barren world, it was already known by that time how much Mars weighed and how big it was. And I'm just giving you here the 1956 values versus the modern values for the mass, the radius, and the mean density of Mars. You don't have to pay too much attention to the absolute values. The take-home message here is that the error in those values were of the order of 1% or 2% with respect to the modern, presumably well-established values. And people were already putting Mars on a mass radius diagram and making the claim that the composition of Mars must resemble that of the Earth. And probably, in fact, it demanded on this position on the mass radius diagram that Mars had an iron core. It was differentiated, unlike the Moon, which was sure at the time had no such core, which was incorrect, of course, but they didn't know that at that time. So, unlike the state of most of exoplanet science at that time, some properties of Mars were extremely precisely established, and such mass radius diagrams were well suited for this kind of investigation. So blasting forwards by 50 years now to the present, we do measure masses and radii of planets. Sometimes they're not the same planets. In some cases, in a few cases, the planets can be measured by both the radial velocity and the transit techniques, giving us the mass and the radius. But for most of these cases, one or another of the measurement, usually the mass, is extremely uncertain. And I'm putting here a plot now of a subsample of perhaps what I would regard as the most interesting planets, which have both mass and radius estimates, or upper limits, on this density versus radius. Now, unlike this plot, its density is increasing to the right, but it's the same idea. And on this plot, which is a logarithmic plot now in density on this scale, you have a number of points here. The solid points are numbers which have actually been measured, and the open points with the arrows are just the upper limits, so that the density must be below this level. And on this plot are also some simple models of the composition of planets. Now, not saying whether or not the planet has to have a core or not, if it's rocky, that is at a precision which is hopeless on this scale. This is just simply saying, is the planet mostly rocky, which would lie up here with no light elements in its atmosphere, or very little. A planet which could have some ice, but also could have a light element like hydrogen in its atmosphere. And then planets down here which our interior structures would indicate that it must have some hydrogen atmosphere. And I've plotted also one of the best, most precisely known objects. This is, by the way, these are Kepler stars, where the error bars are the smallest, where we can actually plot the 2 sigma ellipse, a confidence interval on this plot, and it's not hopelessly big. Pretty much all the other points are worse than this. And you can see that this overlaps between a situation where you demand hydrogen or some very light element in a puffed up atmosphere to one where you could basically explain everything by just rock and ice and some metal. So we are very far from Mars in 50 years ago in terms of this understanding. And I think this is something very important to keep in mind. But of course, remember, this is an opportunity. So what can we learn from the properties of planets? Of course, you have seen from the very many excellent introductory talks how these surveys have provided these planets. In particular, Kepler is sort of the star right now in terms of the number of planets and also the diversity of planets, especially small planets. But as Mars has taught us, ground-based observations have a role, and combining observations can tell us a lot more than Kepler or any space-based transit survey alone. So Kepler tells us the period of the transiting planet, the transiting depth, and then the transit duration. The period we know precisely, the transit depth we know pretty well, and the duration of the transit we know somewhat less well, usually in most cases. So we want to ask these questions, these demographic questions. How many are there? We have to basically go from one transiting system, and as Xavier has talked about, and Courtney has talked about, and Jesse as well, talked about there are these methods to basically interpolate or extrapolate to all the non-transiting systems based on geometric effects as well as the detection efficiency of Kepler or whatever survey you're talking about. And in order to do that, you need to know, essentially, besides the detection completeness, the geometric probability of detection, which involves, by simple math, knowing something about the period, which you know precisely, and what is essentially a free fall time or fundamental oscillation time of the star. This is how Kepler's law folds in with geometry. If you want to know how large the planets are, of course, you need to know, since you know the transit depth, you need to know the radius of the star. You multiply that by the square root of the transit depth, that gives you the radius of the planet. And of course, one of the questions that keeps arising is how hot they are. Or a better way to ask that question probably is how much stellar irradiance they receive. And that just involves the luminosity of the star, the period of the star, and its mass to some extent through Kepler's laws. And so, in addition to what Kepler tells you, you need to know something about the star, specifically the radii, the density, the masses, and the luminosities. You can get the stellar density to some extent from the transit observations alone, of course. So you can write this relation between the observed transit duration, which you measure, that free fall time, which is a function of the stellar density, which is what you want to know, the period of the orbital period of the planet, which you, thanks to Kepler, you know precisely, and then this dimensionless factor, which is a function of orbital parameters, which you don't know very well at all, if at all. And then there is also the effect of limb darkening, which was discussed by Courtney and perhaps other speakers as well, that also to a minor extent influences this relation. So you need to somehow back this out and get take the observations and get this quantity, the free fall time and therefore the density of the star. So the thing that you do is you fit, of course, a light curve model to the data. This just shows some fits by Jonathan Swift and his collaborators. You might not be able to read all these parameters, but these are all the parameters that go into a relatively simple light curve model of a transit, including the limb darkening parameters down here, the interval of the transit duration up here, the period of the transit, and you probably can't read the scales, but some of these are precisely known. But things like the transit duration actually have some uncertainty in them of a few percent or even tens of percent. And these are often very correlated. A few are, of course, precisely known, such as the orbital period. So you know the transit duration to some extent. You can get a posterior distribution of that transit duration from your light curve model. And you actually have to turn that now into density for the star, also accounting for the things you don't know, which is the orbital eccentricity and the other orbital elements. So the basic math behind that is you have to sort of do an integration over those unknown quantities, assuming some perhaps reasonable distribution for those unknown orbital elements. You do this and you get a distribution then, a probabilistic description of the density of the star, not a precisely known number. And this just introduces the math here. You get you essentially boils down to an integral of a quantity over these orbital elements, and it requires some prior assumption of what the distribution of those orbital elements might be. If you put in reasonable distributions, such as a Rayleigh distribution with some mean eccentricity that might be low or might be somewhat larger, depending on what you think that distribution is, you get shapes that look like this. And then this must be convolved then with your distribution of transit duration. So essentially you're taking this and convolving this with that integral that I showed you before to get out a distribution of the stellar densities here. So this is just for one actual real example of a KOI. It happens to be a planet around an M dwarf, but it could be any planet that you like. And you can see here, perhaps to your dismay, that the stellar density varies over quite a bit. And so, of course, stellar density is sensitive to 1 over r cubed, so it's not quite this bad, because ultimately you would like to get r out, so your sensitivity goes down a little bit. But nonetheless, this is perhaps not the optimal way, or as our president would say, this is suboptimal. So you'd like to introduce ground-based techniques or other methods to get those stellar parameters, just blasting through these. These are important to keep in mind. This workshop is not necessarily about these, although maybe that will be some future topic. But astroseismology, which some of you have heard about, is a great way to do it. Kepler has enabled it. But we only know it for a certain number of stars. Not all stars are cooperative. In M dwarfs, it's impossible, unfortunately. There's dynamics. In case of eclipsing binaries, you can, for these few systems, you can actually precisely know the stellar parameters if they also have planets around them. But that's also an elite subsample. And then there's spectroscopy, which is my favorite, but of course can be expensive. Kepler stars are faint, they're far away, and this consumes a lot of telescope time on big telescopes. But you can know quite a bit about the stars from that. And then what we end up as a default value in many cases is simply broadband photometry, the colors of the stars, and trying to do some basic property like effective temperature and then extrapolating all the rest based either on observations of nearby stars or simply on models. Now, one thing that is a missing factor in here, which will change for most stars for which we know planets are around, is the distance. Distance in apparent magnitude gives you basically luminosity. Unfortunately, for most stars, we don't know that distance yet, but that will change now that Gaia has been launched and is surveying the sky. And it will address a lot of the questions that we have about the properties of stars. So Gaia will find planets. There are planets we already know about, but we will know them again anew because we will know their properties much more precisely thanks to those parallaxes. And this will address some very nasty effects that appears, for example, in the Kepler survey, such as Malmquist bias. You think your star is at this distance, and your star is this big, and therefore your planet is proportionally this big, because you know the radius ratio, right? But actually it's out here, further away, because the statistics say there's about 8 times as many stars for twice the distance. So if there is some uncertainty, the tail of that uncertainty is going to be driving you out to further distances. So many of the stars that Kepler is observing that we thought were dwarfs are actually more luminous, older subgiants that have evolved slightly off the main sequence. We know they're there, but we don't know which ones in many cases. So your uncertainties are very asymmetric. This main sequence diagram showing some of the, basically all of the KOIs in the year 2013 that we knew about. Only some of the error bars are plotted here just to keep it from being a mess. You would like to be down here on the main sequence. That's the nominal position, but the uncertainties span all the way up into the subgiants. Gaia will basically make this problem go away for the most part. There's some issues of multiplicity, which it will not address directly for all stars, although for some it will. To give you just a visceral sense of what Gaia will do, these are the error bars. If you just derive the properties based on stellar colors alone, without distance information, and when you take the same sample and you simulate what you would know once the Gaia parallaxes are provided to you, the error bars do this. So they're still there. There's still wiggle room for your models. The modelers can breathe a sigh of relief. We won't test you too hard. But we're now talking about some serious exoplanet science that can be done with this. But again, that's not the whole picture. Suppose you look now at your star for which you have your precisely known Gaia parallax. You know, you have a spectrum, and you go, okay, I know everything. And then you go ahead and do what Jorge did for many of these stars and take a high-resolution image, and you see, oh no, there's another star, maybe a fainter star. And now you're really upset because there's a couple possibilities here. One is that, all right, you're going to have to take into account the light from this other star that dilutes the transit signal. So your planet is actually bigger than you've previously thought by an amount by that dilution factor. Or, since Kepler has 4 arcsecond pixels, and even with the precise astrometry it can do, it can't distinguish in all cases based on the motion of the centroid of the light. You don't know which star the planet is around. So this is difficult. But again, you have, based on your measurements of stellar properties, some estimate of the properties of the star based on the transit, that stellar density profile, probabilistic distribution I showed. You take a spectrum and you do the same thing, and you can compare the two. So this is an example for, again, the M dwarfs, it just turns out to be, of a system where there's 2 stars, a primary and a fainter companion, and you can get different probabilistic distributions for the density based on your fitting the transit and based on the spectrum. So the spectrum is a nice Gaussian, because we assume Gaussian errors, which is not too far off. And you can see that in the case of this system, the primary, the blue ones, both the transit duration and the spectrum-derived densities agree. However, they do not agree for the case of the companion. So if you put around the planet around the companion star, there is no consistency. You have to assume a very, very high eccentricity, which is possible but not likely, or you just simply say it's around the primary. So this is a case where we can distinguish based on a complementary synergistic observations, a very important thing, which star is the planet around. In other cases, we're not so fortunate, and they both overlap. And stars, of course, of equal brightness at equal distance have essentially identical properties, and you can't say. You have to adjust the planet radius, and maybe you don't care which star it is around at that point, but if you did, you would be out of luck. So I want to end my talk today with just a couple more slides. Since we're talking about demographics, this is changing gears a bit, but since the topic of demographics is the sort of highlight of this conference, I think this is relevant. There was a discussion about the 2 major types of deducing your planet population. One was by this method, which is binning. You basically take your planets that you observe, you distribute them in orbital period and planet radius, and you construct bins around which you count the planets. You calculate the completeness of your survey, in each of those bins, and then you divide essentially by that completeness to give you the intrinsic planet population in that bin, and then you can go from there. So this is two classic works now, Eric Pettigura's work and Andrew Howard's earlier work, showing the distribution with either planet orbital period, planet radius, or just planet radius here on this, showing the bins very clearly here. Or, as Jesse talked about, you can do the parametric approach, where you assume a smooth distribution with some power law distribution or whatever you would like, but you of course have to make an assumption about what that shape or what that function is. So this is a way of avoiding both of those limitations. You don't have to bin here, and you don't have to assume anything parametric. There are certain assumptions that you may have to make, although you may make, but not necessarily, like whether or not your planet population depends on the intrinsic properties of the star, or whether all stars are treated equally. So this basically is what I call the method of iterative Monte Carlo, or MIMIC, so you can remember it. It actually has a longer name, which I'm not going to say here in public, but it's less memorable. But there is a mathematical history to this. But we took it, we borrowed it or adopted it for the purpose of detecting or inferring the planet population around stars. So essentially it's a Monte Carlo method where you iterate until you get the answer. It's very, very simple. It's actually something I encourage you to do at home because it is really, really trivial. You take a trial population, you run that through a model of your detection, of your survey. You get out simulated detections from that, of course. You take a random subset of the trial population and you replace that with the simulated detections. And you continue this process ad nauseum until what you're replacing is essentially indistinguishable from what you're replacing it with statistically. And at that point, your inferred population is giving you essentially the simulated detections which match the observations. And as long as your detection model is accurate, accurately representing reality, then this population here that you've been running is the inferred population. And if you don't believe that, you can read one of the papers we've published that uses this method. You can stick in a trial population or an inferred population. You can simulate the detection efficiency, say, of Kepler to get out a series of observations, and then you can run this method, MIMIC, to back out the inferred population, which basically reproduces that distribution which you knew about because you faked the planet population to begin with. This, of course, is binned in this, but we get to choose the bins. So my concern with the binning techniques is, of course, you do not know a priori where nature may put boundaries or not. So for example, this drop here at about 2.8 Earth radii, is this real? Or is this just a fortuitous product of the way that we bin the data and there were just a few more planets here and not as many planets here? So you can choose to bin the data afterwards as you wish because you want to make nice histograms to show people, right? But that comes after the fact. What you get out is an inferred population that actually can be much larger in terms of the number of simulations that you're doing than the actual observations that you have, and then you can smooth it as you wish. I think that's it. The last slide just basically is taking your measure of, say, the parameters that you've found for these planets, the radius and the orbital period, which you know, or the irradiance, which you can calculate, knowing the luminosities of these stars, now that you have the Gaia parallax. And then you can, as was mentioned earlier, do things like test population synthesis models. You can make predictions about what future surveys, such as Plateau or TESS, will find. And of course, you want to construct mass radius diagrams and test interior models to say what these planets are made of, which may ultimately lead you to calculations of the number of Earth-like planets out there, which of course we're all very interested in. But remember Carl's admonition, be very careful about separating fact from speculation. Thank you very much. Yeah, no, you're only, yeah, so the question, I'm not sure, okay, so the question is how can this work? Given that you're replacing this, the random, you're replacing a random subset by the simulated detections. What you're actually doing here is what I should be clear, maybe this is the misunderstanding. What the random subset is basically the simulated detections down here. This is the random subset. The randomness is referring to the simulated here. So you're replacing those trial populations ones which have been detected by these simulated detections here. Randomly chosen. And then you can mix them, if you wish, amongst the stars. You can randomize among the stars.
So you're not choosing different random subsets for each iteration within a trial?
That's right. The intrinsic thing is which ones are getting detected, right? So you essentially were replacing these so that eventually the simulated detections that you're getting out resemble the ones that are being replaced by the actual observations. So that random subset is the ones that are being, yeah, the question is, if this is a random subset of detections, let's say, if this is a radius period diagram, for example, or some parameter space, are these the same ones that are being detected? The answer is no. No. So these are constantly being, depending on which ones are being detected, those get replaced with randomly selected observations. So this box is not really a box, it's a subset.